So our recording has begun. Again, welcome. Thanks everybody for joining me in this next section of our online live seminars, Siemens seminars. Today we're going to be talking about G-code programming with ProgramGuide for milling. I am going to be your presenter, Chris Pollock. My information is here up on the screen for you guys. I am a dealer support specialist with Siemens. I cover the East Coast territory. So specifically, I'm here working with any OEMs, importers, distributors, anybody selling and supporting the Siemens product. I am here as a resource for them, as well as any of you end users out there that have some questions. By all means, you can always feel free to reach out to me at either the email there on the screen or on my phone. Probably the best way to get a hold of me usually is email, but certainly both are available. So we got a couple more coming up, just as a quick little teaser, just to let you guys know what we're doing in the future. The next planned seminar is going to be June 19th, and that is going to be starting to look at 5-axis shop floor programming, specifically with shop mill. So it'll be 3+2 style programming in a 5-axis machine tool. So we'll be basically positioning like a trunnion table style configuration around in a 5-axis orientation, and then doing 3-axis cutter path on the surfaces. But we're going to be programming everything conversationally as if it was right at the shop floor through our shop mill. And then after that, we are going to do, in August, we're going to do a basic setup and programming for turning on the 808 control, the newest of our control platform. So today, specifically, we're going to be looking at the 828 and the 840. So really anything that we talk about, we use today, although could possibly apply to the 808 control, specifically will run and work in the 828 and the 840 product line. So if that's the products you're servicing, supporting, or using, this will apply specifically. And then, like I said, if you're running one of the other versions of the control, majority of this stuff that we're going to look at today is pretty much universal. So it should even transfer over to the other platforms as well. So this is just a quick overview that you guys should have seen on the initial promote of the series, just covering some of the basic things we're going to be doing today. In a nutshell, we're going to take a nice little simple two-dimensional job, a little milling job with some drilling and some counterboring, and we're going to get a chance to kind of methodize that twice. So the first time we're going to do it, kind of simple steps, going through just real basic G&M code type of structure. And then the second time, we're going to start to show you some of the advanced cycles. We'll do some calls to outside subprograms and just show you a few tricks within the system to be able to play. It'll be the same job or same part program, just in 2 examples. So this is the part profile we are going to be working on today. Just a simple irregular shape, nothing too complicated. So we're going to get a chance to profile mill the part, handle some arcs, handle some corner breaks like chamfers and radiuses. Once we've profile milled it, we'll certainly go in and drill the holes, put a bolt hole pattern to it, or shall I say a counterbore into that pattern of 4 holes. Then we're going to even come back and do a quick little chamfering operation on it, and we'll look at a couple different scenarios of how you would handle that. First area I want to kind of take a look at this morning is, or shall I say this afternoon, is offset and the offset table and setup mode. Kind of want to delve into a little bit more detail on creating tools. We've certainly covered doing some basic setup and some basic tool creation in some previous webinars. So I'm not going to spend a lot of time going through what we've already covered, but I want to start to talk about maybe some additional functions and features within those areas. So with that being said, we're going to go and create some tools, start to look at the tool library in a little more detail. We're going to look at some more advanced tools like base mills, taper mills that may require a little bit more additional information. So here you're going to get to explore the further data function, start to see where all this additional information kind of comes into play. Since this is a G-code-centric class or session, we're then going to talk about MDI, MDA, MDI as we like to call it. we'll play around just doing a couple basic instructions to maybe get the machine to do tool changes or fire up the spindle, whatnot, as if I was, going to be preparatorily getting ready to possibly set up a tool, set an offset. So you get a chance to see a little bit of the features of MDI and kind of how that works. And then from there, I don't want to spend much time on it because I have covered it in other sessions, but the next logical step would then be go in there and set your workpiece or measure your tool. So these are a couple of the functions we would certainly use to then establish those offsets. So what we're going to do now is we're going to actually transition over to a piece of software we call Sinutrain. And Sinutrain, as we've used in the previous sessions, is like a machine tool emulator. So it's going to allow us to actually mimic all the steps that we would do on the machine. So I'm going to bring up Sinutrain right now. It should all be displayed for you on the screen. This is the same tool we've been using all along for these sessions. So this is going to handle really emulating how a machine tool would run. So everything I can do on the machine tool, I can do here through Sinutrain. So right now, we first launched Sinutrain. We are launched in a jog scenario. This is generally the first screen you see when you power up Sinutrain, and it is also typically the first screen you see when you power up your machine tool. Our machine control panel is not fully live here, so I'm going to have the opportunity to adjust my overrides, maybe set some enables, start to run the machine. And if you refer to some of the previous webinars, we go into a lot of this in more detail on how to move the machine around and use this piece of software. But as I said earlier, we are going to want to kind of jump right into maybe creating some tools, looking at MDI, making some functions happen. So the first thing I want to do is I want to go to the offset page. And the offset page contains all of our tool data as well as all of our work set offset data. So I use the offset button. And my offset button is right here in my little keypad in the upper right-hand corner, just above my blue arrows, my 4 arrows. You'll see the button called Offset. Depending on your machine tool, the layout may be slightly different, but these functions all exist. Some builders like to use custom front panels or kind of really move things around. If you're having trouble navigating the machine control panel because of the differences from builder to builder, one of the easy tricks is just find the menu select key. Here you'll see I have a menu select key in the lower corner of that little keypad. Menu select gives you all of these buttons as well as all of your mode buttons like jog and auto and MDI just on the screen as a soft button. So if you're having trouble navigating, having trouble finding the buttons you're looking for based on the layout that the builder did, once you find menu select and kind of associate yourself with where that is, you can navigate through the control pretty quickly. Just use menu select, and then I can get to my offset screen, which we call parameters as the soft key here. I can go to Program Manager. I can go back to Machine. If I go to the wrong machine mode, I can always jump back to menu select. Maybe I want to go to auto. So you'll be able to bounce around pretty quickly just with the menu select key. I find myself on a lot of different configurations of front panels, so it's certainly a trick that I use quite a bit. Right now, there are some tools already pre-created in our tool library. I'm going to delete a few. We're going to go through some basic steps of building a few tools. So let's just come in here. Some of these are from earlier scenarios. Okay, we'll delete our 7/16 drill because we're going to make that here in a second. And we'll delete this end mill. We'll leave a few created for later. Yes, I really want to delete you. Okay. So when it's time to start building tools, I'm going to look at my job. I'm going to kind of figure out how I want to methodize my part. I'm going to certainly come up with a series of tools that I want to build or create. You're going to come to the offset table, and you're going to do one of two things. You're either going to build tools in a loaded state. That is a tool physically having a number to the left. This would be representing a pocket location in your tool changer. Or I can build them in an unloaded state. So here you see I have a whole host of different tools in my library down in this bottom state. So that's just a tool that exists in memory, but it's not physically in the machine tool right now. So you can build them in either area. Some builders force you to build them in an unloaded state and then go through a loading mechanism. There's nothing wrong with that. That's just part of their safety standards. So if that's the case on the machine you're specifically finding yourself on, you will have to come down here to the unloaded section to get the new tool button. If you're on a machine that the builder allows you to build right in the tool magazine, then you can be at any blank spot and select the New Tool button. So the first tool we're going to build for our first example here is going to be a 3/4 inch end mill. But what I wanted to show you is, you're going to start using naming nomenclature. It's a pretty popular and powerful feature within the Siemens control, being able to call a tool a name instead of a number. But a lot of guys still have issues with that, whether they're using a CAM system and the CAM system can't output names, or they're used to their process. Their process doesn't use these names like cutter or end mill or whatever I want to call it. Well, if I want to call a tool a number, I absolutely can. Nobody says you have to use a name. So for this sake, if I wanted to create tool number 1, and tool number 1 is going to be a 3/4 inch end mill, I'm just going to name it number 1. And then when we get to the programming section, you'll see how I call it up with a T code. When I'm building the tool, the length isn't as important because that will get set up for me when I go to actually measure the tool with the different utilities within Jog. But I do need to give it the diameter of the cutter. So I am going to want to type in. This may be radial on your control. It can be changed. Basically, what you want to look at this top field. See how this little symbol at the top of the row here shows a diameter? That's signifying to me that this machine was commissioned to support diameters for its tools. If a builder decides to go radial, then it will represent a radial scenario, and you would put the radius of the tool here, obviously half that. The only other thing I need to fill out for this tool specifically would be my number of teeth or number of flutes. So let's say, for argument's sake, I had a 3-flute cutter. I'll type in the number 3 here in this field. Then it will default the rotation and or give me the ability of turning coolant on or off. These 3 fields right here are only going to help you in shop mill. So if you're G-code programming, this isn't a required area. In fact, it won't even look at it because we are going to give it those statements within the G-code program. So when I'm building tools, especially for G-code, I'm really just worried about number of flutes, only if I'm going to really program feed per tooth, and we will do that a little later to show you how to do that. The diameter, the length when it's time to set. Now we do have the D here. The D stands for multiple cutting edges. Maybe if we have time later, we can look at that a little bit. And then the ST, the sister tool, that would be if I want to do tool life management and I want to associate tools, I would create sister tools. Okay, so certainly a simple tool created. In this case, we have a 3/4 inch MO called number 1. Next tool we're going to use in the program, might as well build it now, is a drill. So I did want to just talk about and show you guys how to build a drill real quick, because there's a couple extra questions or different questions when you get to a drill. Now, right now I'm in the favorites section. I can also go deeper into cutters or into drill and get to a larger number of combinations of tools. We even have special tools if I want to get to more elaborate tools like probes, star probes, slotting tools. So I can really build in from wherever I want. Favorites is just a condensed, what we consider, like the top 10 kind of scenario, the most commonly used tools. You can't customize this. It is a fixed favorites. So if I select twist drill, I'm now going to be building a twist drill. Say OK. My system's set up for the default naming. That's an option, or not even an option, but that's just a setting in the back end. So whether you wanted it to or not, if you have that turned off, it'll just come up with a blank name. But let's say, for argument's sake, I wanted to call this a 17/64 drill. Oops, I want to put my cap blocks on. Not that it matters, but I like the look of it better. So we type in the name of the tool. Once we've typed in the name of the tool, on the machine tool, you're going to physically hit the input key. That's this yellow key to the right of the keyboard, the keypad. For me, I don't have to actually hit that if I don't want to. I can just hit the enter key on my keyboard. It does the same thing. Now, anywhere there's a numerical field here, I can either type directly into the field if I want to do basic math, or I can select my equals button on my keyboard, and it'll bring up a calculator for you. So either way, if I didn't know the decimal equivalent, but I wanted to give it for a 17/64 drill, I can type the field in. Now you will notice, however, it also gives us tip angle. Tip angle is important, and you're going to see it when we get into doing the drilling cycle. The system can compensate for the tip of the tool. So in my case, I wanted to build this as a 140-degree tool tip angle, so I'm going to type in 140. Other than that, there's nothing else I would need for a given drill. We are going to be using a 3/8 end mill in this job. I happen to have left that one pre-created, so that would have worked the exact same way we saw before. And then we are going to use a center drill a little later. Center drill is going to build a drill exactly like a drill does. The only difference is a center drill will default the included angle of the drill to 90 degrees, like a traditional NC spot drill. Certainly I could put 82, or I could put whatever would match it. So this would be a good drill if I was using it for countersinking, or what we're actually going to use it for is chamfering. Okay, so we build up these tools. Now the next step, talking about in the flavor of G-code, wanting to maybe do some tool changes, would be potentially going to a function called MDI or MDA. We historically always called it MDA, MDA standing for Machine Data Automatic. You'll see even on the button it says MDA. But the industry terminology has always been MDI, Machine Data Input, so we've kind of adopted both. The reason being why we came up with Machine Data Automatic in the past is it was really a differentiator from us to our competitors, because our MDI has always done probably a little bit more than you'll find most competitive controls do. This is a full automatic mode. So I can come in here, I can do multi-block or multi-line programs. I can load or save the program. So I can go to outside memory if I had pre-created scenarios or examples, like little MDI programs I like to use a lot, and I can just load them in and they'd automatically propagate in here. So there's really not a whole lot of difference between MDI and our full auto mode, and that was why we always kind of called it something a little different. So in this case, if I look at my TFS window, as we've seen from earlier webinars, this is where I can kind of track what tools in my spindle, what feeds I'm doing, what state my spindle's in. So let's say I wanted to do a tool change. Now, traditionally with this control, we're used to being in Jog and using the TSM field. But if I want to do a tool change inside of MDI or in G-code, I'm going to type a T and then the name of the tool. So if it's a number, like you just saw before, I would type the physical number of the tool. The D1 calls up its offset 1. That was that first D field that was to the right next to the sister tools. I issue my M6, typo there, to initiate my tool change. And then I give it an end of program. And end of program could be a couple different things. I'm going to use an M30 for this first example. By cycle starting the machine, she's going to go up, she's going to do a tool change. Initiate a tool change, Z would have moved up, it would have swung the carousel and did all the operations it needs to perform a tool change. Now I see tool 1 is in the spindle. Now what happens if I wanted to tool change to my 3/8 end mill right here? Well, now the terminology or the nomenclature changes slightly. So I'm going to cheat, and I'm actually going to copy the name here. And you can even do this on a machine if you wanted to. And I'm going to jump back over to MDI. So if I want a tool change to named tools, not tools that just have a specific number, it's going to look like this. It's going to be T equals, and then inside quotation marks, I'm going to have the name of that tool. And that's also going to be how you see it build on the machine. So here, T equals, in this case, 3/8 end mill, cycle start. Now we see the 3/8 end mill into the spindle. Now, as well, with changing a tool, I may want to start my spindle. So I give it an M3 for spindle clockwise, give it an S statement for whatever I want the RPM to run. Now, we have a little trick here. Normally, if I just issue this line by itself and I hit cycle start, the spindle will start running, as I see here. I got an RPM issued of S1000. I see my little encoder display spinning around. But what happens is we're not in a reset state. So right now it's still kind of hung in a program mode. So if I was to go back over to Jog, because I wanted to get to that measure workpiece or measure tool functionality, see how specifically the measure workpiece, all these functions are grayed out? It's because I'm not in a reset state. Right here, if you look just above the work field, it even tells you you're interrupted, meaning it's still running a program. So if I hit reset, that clears that, but it also shuts my spindle back off. If you were back over an MDI and I gave it an M30 to put the machine into a reset state, that would work as well, but the M30 would shut the spindle right back off because M30s and M2s shut the spindle off at the end of the program for you automatically. So we have a little trick here. There's a M code called M32. And M32 is an end of program, but it will leave the state of the spindle in whatever state it's in. So in this case, if my spindle is running with an M3, S1000, it stays on. If I go back to jog, I'm in a reset state. It says I'm in a reset state, but the spindle is left running. So if you want to be able to fire up a spindle and then go use an edge finder, go to measure workpiece and go find the edge of a part, let's say, you do have to give it an M32 at the end of the program to keep it running yet reset its state. Other than that, there's not too many tricks here. You can certainly do all kinds of little features and create some custom routines. So like I was saying earlier, if I like this program, if this was elaborate enough, that's something I did a lot, I could just hit save, tell it where I want to save. I'll just put it in the part programs directory and then give it a name. So I could call it spindle on. Say OK. Now, if I go to load, there's this little spindle on program. I say OK, puts it back into memory, overwrites what was there. In this case, it had the same thing. And away we go. OK. So that's a basic overview on our offset table. We're going to go and spend a lot more time in detail in the offset table as we kind of move through the part programming. But what I do want to do is I want to transition to our next section of slides or PowerPoint, because we're going to start to talk about creating a part program. And I want to get in there as soon as we can because we got a lot of stuff to get through. Okay, so we're going to start doing our Program Manager Example 1. And the first thing we're going to do is we're going to go in and we're going to physically create a part program. So we're going to start to look at the Program Manager section, and we're going to physically create a given program. So from there, once we come to Program Manager, we'll look at our NC memory, and we'll talk about what it takes to build a G-code-based program. So in this case, we'll select New Program, pick a directory, or maybe a point where we want to save these programs to, and then type in the file and initiate a G-code program. Now, I did give you guys, and I don't know how many guys noticed it, but there was a handout included with this seminar. And this is just a nice little, kind of like a cheat sheet I like to use or I like to give out when starting to write G-code programs. I had given it out on the lathe one. The sheet kind of covers both milling and turning. So for those of you, if you missed it and you would like to get it, certainly you can always email me and I can send it to you directly. You can probably, if you go back to the registration page as well, still gain access to that, I believe, but I haven't actually tried that myself while we're in this session. But what this is this just an overall kind of worksheet as to step you through the basic mechanism of building either a milling program or a turning program, and then our little cheat sheet of commonly used G and M codes within our world on the back side of that. So you will want to get that if you didn't happen to grab it already. So once we've initiated a new part program, we're then going to be into Program Editor, and we're going to start to create a program. So the first section of program we're actually going to build, we're going to do that longhand. So we're not going to use any CAN cycles. We're actually going to program around a part with lines and arcs and round corner functions. So you're going to get to see a whole host of different commands, rapid commands and feed commands, non-modal statements, like we see this Z equals IC function. We're going to get a chance to play with that for a minute or two to create like an incremental loop in my Z if I want to take multiple steps of cutting the Z. We're going to turn on cutter comp using a G41 statement, shut it back off to 40. We're going to do an arc, and we're going to use an arc. We have many different ways to create arcs within our control. We're just going to use one example, which would be an endpoint and a radius. We're going to do corner chamfers and corner radiuses using our CHR command or our RND command. And then we'll even use the repeat function to be able to loop and get multiple cuts out of the part. Once we've done the milling profile, then we're going to just jump into our drilling cycles. You're going to get to see how we can build drilling cycles. We have conversational, what we call data masks, supporting G-code. So you don't actually have to ever write the cycles in any great detail. You would just physically come in and enter the data mask, the conversational page, fill it out, and it'll build you the cycle call like you see the results. So we have can cycles, pattern cycles. We're going to get a chance to explore both of them. Then once we've gotten that in, we'll certainly jump over to our simulation and explore how well this is cutting as if it's doing what we're expecting it to do. And we can look at simulation in a few different methods, 3D, sectional views. Specifically, we'll probably point out how we do some simple chamfers and stuff with that center drill. So if we switch back over to Sinutrain, should be back up on our screen where we last left it. And what we're going to do right now is we're going to jump over to Program Manager. We're going to start building our part programs. So I'm going to want to be in my NC directory. That's my standard directory. I can build programs in my part program folder, or I can go into work pieces and certainly build programs in subfolders if I'd like. We'll just stay in part programs for this example. I'm going to select New, because we're now going to start creating a program. Now, depending on your machine, you may or may not have shop manual, but you will always have ProgramGuide for G-code. So this is a standard feature. Everything you're going to see here is actually all standard. None of this is optional at all. So anything we see here, you should have on your machine and should be currently working. So we go into ProgramGuide. We want to make sure this radio button is selected, and we type a name. So I'm going to call mine example 1. When naming, letters, numbers, underscores. The only 3 types of characters we support. We support, I believe, up to 24 characters here, so you can put a pretty big name in it, but we don't want any spaces, minus signs, forward slashes. In fact, if you try it, it'll say it's an unrecognized character. So like in this example, if I wanted a space between the name and the number, just put an underscore. You do not have to put the extension. MPF stands for main program file. That will automatically get inserted for you if I'm doing subs, and we are going to see the subs later, and then there are SPF extensions. We can see that when we get to that point. So I select the name of my file, say OK, and we are now in our editor. So when we first start a basic G-code program, and this is kind of where that little sheet gets handy, you do want to start with what we call like a safe start, just some basic modal commands that we would initially turn on, and we would want active for the length of the program. So a very normal scenario would be like telling the machine I'm in a G17. G17 is the orientation of the tool. So in what direction is the end mill pointing or the drill pointing? Is it pointing parallel to the Z-axis, or is it pointing relative to an X or a Y-axis? Traditionally in a 3-axis mill, you're in a G17 orientation, so that would be your default plane. G90 or G91. G90 stands for absolute positioning as opposed to incremental positioning. So we're going to do all programming today absolute, at least from a modal standpoint. G54 would be my work coordinates. So which of my offsets am I writing to, or do I want to call from? So this is my part 0. And then do I want to be in an inch mode? Do I want to be in a metric mode? So I'm going to use, now we do have 2 different ways to stipulate inch, or 2 different ways to stipulate metric. We have G70 or 700. Both are defining that the control be in inch mode, or we have a G71 or 710. Both would be defining that I'm in a metric mode. Why do we have 2? What's the base difference? Well, if I'm in a G70, that's telling us that all the dimensions within this part program are going to be an inch. But it is relying on whatever state the machine is currently sitting in back here, like in Jog, to be in the mode. So for argument's sake, if the machine was sitting in metric, yet I was writing a program here in inch mode, it would actually apply all my feed rates in metric. So if you're a guy that maybe you're doing the opposite, machine's sitting in inch mode, but I have to write a metric program, but it's hard to think feed and speed in metric, you could actually do a G71 and leave the machine sitting in an inch mode. And when I do a feed rate, the feed would be like an F of 10 would be actually 10 inches per minute, not millimeters per minute. So normally, I always train guys, just use 700 and 710. This way you are not kind of slave to whatever mode the controller or the machine is sitting in. That's saying that all dimensions, all feeds and speeds, and the entire length of the program, in this case, are going to be inch. Now, the next statement would potentially be what we call our workpiece statement, workpiece line. That's what sets up the 3D model. for our simulation, but I'm going to leave that off for now because I do want to show you how to just simulate basic wireframe first, and then we can come back and look at the 3D. So the next step would be traditionally load up my tool, tell it what tool I'm going to use. So we had previously built a tool, and we knew it was built as T1, and that's our 3/4 inch end mill. So I type in T1, get in the habit of using D1, calling up the first offset. And this has no correlation to the T1. No matter what the name is, you'll see it further down. You're just going to call D1 for the first cutting edge of the tool. Give the machine a tool change. Maybe fire up my spindle, some RPM. I do not need the leading zeros. If you like it, you can put it. You don't have to. So I could have put an M03 or not. You can do multiple M codes on the same line. So maybe I want coolant running on this job. I can type that. I can now tell it what the rate of feed is and the type of feed. So we have G94, which is inches per minute, or G95, which would be feed per revolution, and that's per revolution of the spindle. So in this case, I want to be in inches per minute. I give it an F to signify the feed rate that I want to run, and then some speed. So let's say I was going to run 50 inches per minute. From there, my next line is probably going to be a pre-position physically onto the part or somewhere close to the part. Now, one thing I do want to do real quick is I want to bring up the print here. So let me just grab that. Everybody should have that. So I want to keep this kind of in the corner of the screen there for you so you can kind of get a visual of what I'm doing, of what we're doing. So in this part, I'm going to treat the upper left-hand corner as 0, 0. That's where all my dimensioning was from. And then we're going to walk around this profile. We're going to walk around it in a clockwise direction. So we're climb milling, machining out this part. So most likely I'm going to want to pre-position my tool somewhere off that corner. So I'm going to do a rapid. Maybe I want to be, I don't know, X -1 to the left of my 0, and a Y +1 up top, and maybe my Z, I'll bring all 3 down in one shot. So that gets into position. Now I'm going to do a G1, signifying a feed move as opposed to a rapid move from the G0. And let's say we want to bring our Z down into our part for our cut. So I'm going to come down 1/4 inch. Once I've brought the tool into position, I can now start actually moving around the part. So from here, it's really a matter of just giving it line moves or arc moves and describing the shape of the part I want to physically cut. So I'm going to tell the machine to position to my corner, my 0, 0. Now, G1s, G0s, they're what we call modal statements. Modal meaning they're going to stay on for until I tell it otherwise. So I don't have to keep typing G1 on every single line. I can just put it on that first one, and then only when I've changed it to like the rapid mode, or you'll see it in the arc, do I have to go back to a feed mode. Now, I do want to turn cutter comp on here, so I'm positioning the corner, and this is when the system will initially turn on my cutter comp. G41 is cutter comp left, 42 is cutter comp right, 40 would be cutter comp off. So what is that going to do for me? Well, I'm going to position the true geometry of the part. The cutter comp will actually move the cutter over by whatever the radius of the tool is and make sure that it stays on the outside of this part. How do I know 41 or 42? It's actually pretty easy. As long as you know the difference between climb milling and conventional milling, you always have to be in G41 if you're climb milling. So no matter whether you're in a pocket or a profile, the direction of cutter path actually goes backwards in a pocket. But if I'm climb milling, it has to be G41. You can't climb mill in G42 mode. Some other people like to keep in their mind that if I was the end mill walking the path of this cut, then what side am I on in relation to the part? I would be on the left side, G41, cutter comp left. Okay, so we've gotten into position, we're on our part. Now I'm going to be doing my first move. So if I look at my part print, in fact, a X of 2 inch will get me to the start of an arc. So I'm going to just move over X of 2. Now we're going to sweep an arc. Now I need to use an arc statement here, either a G2 or G3, G2 standing for a clockwise direction arc, which is what we're going to use. If I was going the other way, it would be counterclockwise, it would be a G3. So I type in my G2. I don't need the 0. I can put it if I want. Then I tell it the end point of my arc. So dimensionally, I see that's 3.250. and a y of minus 0.671. I see on my dimension. So I put my minus 0.671. And now I have to stipulate the radius of this arc. So that in our world is a CR equals statement, and then just the radius. Some competitive controls, we're used to just putting an R and then the value. Oops, typo. In ours, it's a CR equals. So I type in the arc statement. Now we are going to be doing a move, and we're going to be coming down this back slope. So I'm going to be going back to a feed move or a linear move. That's a G1, linear feed move. And I'm going to position two axes at the same time. So X is going all the way over to a 4-inch value. Y is going to a minus 1.082. 82. All right. And that simply just by telling it two moves from the same line, I get a 2-axis move, or in this case, a taper. Once we've positioned the tool down that slope, I'm now going to move, and again, I'm in modal, so I don't have to keep saying the G1. I'm going to move Y down all the way to the bottom, which is a minus 3 inches. But when I get to that point, I actually want to do a chamfer. So I can do what we call an end-of-line chamfer or radius statement by simply typing CHR equals and then the size of the chamfer. And the system will automatically, in this case, apply a 45-degree chamfer between this move and whatever comes next, which in this case is going to be a X move to a value of 1 inch. Now that's going to be positioning right along this bottom slope, right to the intersection of two lines. So now I want to blend a 1/2 inch radius. So it's the same kind of function you just saw, but it's RND equals, and then give it the size of the radius. We can now do a 2-axis move, X going to 0, Y going to minus 1.5, and we can do the same thing. We're going to have an R and D equals another 1/2 inch. Once we got that radius there, I'm now going to move up. So we're going to go to a Y0. All right. Completes us to the top of the part. Now, when you're doing this longhand, I do want to kind of pull off the part and shut my cutter comp off. So I'm just going to position back to where we started from. So I'm going to go back to X of minus 1, Y of positive 1, and I'm going to shut my cutter comp off with a G40 statement. All right. So what I'm going to do is I'm going to throw in a quick little M30. M30 signifies end of programming, and we're going to simulate this real quick just so you can see kind of what's going to happen. So by launching simulation, we're going to come in, and we're going to see a cutter come down and start walking around our part. Now, see how I saw the cutter moving around, but I don't have anything on my screen. Well, since I haven't put the blank in, I'm not going to get any of my 3D modeling. But that's okay, because a lot of times, we'll get a program in from CAD/CAM and it doesn't have any of that stuff set up. If you simply hit the double arrow over here to modify your vertical soft keys and click on the Show Toolpath button, we get the wireframe that we're doing. So if I back up, recycle start, and looks like I might have had a typo in my radius there. It's not, doesn't look tangent. So we can take a look at that real quick. But let me just zoom in, and we can start to see that would be the center line of the cutter path. Now, I'm probably going to want to see it a little better. I'm probably going to want to see it with the solid model. So the simplest way to get that to work is if I jump back into my program, and I'm going to position my cursor right at the top of the program. Under our various button, we have a function called blank. And blank allows me to describe a whole series of different types of blobs that would represent the stock. So cylinders, pipes, a block with the center of it being 0, 0, a block with two opposing corners. So that's what we've set up for this one. I have some predefined numbers here. So that would just be, you define 2 points. So I use the upper left-hand corner, something a little off the part, the lower right-hand corner, and how thick it is. So you fill this in, you hit accept, and it sets up this cycle called workpiece. So now if we go to simulate, now we should see it working around our part. So there we are. All right, so I see I do have something there, probably a bad typo. I was supposed to go to minus 1.802. I bet you I didn't go that far down. Yeah, 1 point typo. Look at that. Gotta love simulation. All right. So I can make my change. We can re-simulate our part real fast, and we should start to see a little bit nicer tangent arc. There you go. So this scenario obviously is taking it all in one shot, and we can do that, but that might not be the most desirable method. In fact, if you look at it in 3D, I'm only taking a 1/4 inch deep cut. I'm taking it all in one shot. Well, we have a trick here that you can start to use, and it's using a repeat function, and it's also using a function called a non-modal incremental shift. So what I'm going to show you here real fast is instead of positioning right here to my 1/4 inch down, I'm going to position to Z0. And then my next move, my next line, is again still going to be a feed move. I can put it or not, doesn't matter. And I'm going to tell my Z, and I'm going to put a new statement. I'm going to say Z equals IC, standing for incremental position. Oops, I don't need this bracket there. IC, and then in parentheses, the distance I want to move down for every cut. So I'm going to tell it minus 0.125. So now, machine's going to rapid, 100th out above, feed to 0, and then it's going to incrementally move down 125. So the first one would be no different than if it was an absolute position. This is where the trick comes in. So I wanted to get sequence numbers, so I have some way of repeating. So I'm going to hit my double arrow over and hit the renumbering button. Renumbering will allow me to place end numbers automatically in my program. Then down here, I'm going to put a quick little statement, and I'm going to say repeat, R-E-P-E-A-T, and I can use sequence numbers. So I'm going to repeat N. I'm going to go back to where my incremental shift was. So N45, 2, and I want to repeat right down to N90. Now, if I just do it once, this will only do 2 cuts. So 1/8 inch down, and then repeats back up, does again. But now I can loop it if I want. And I can loop it by giving it a P equals and tell it the number of times I want to loop around. So simply P equals and a number, that will cause this to repeat. So now as we start to run it, we're going to start to see we're taking 1/8 of an inch per cut. Once around, there's our second loop, third loop, and our fourth final. So why did I get 4? Well, because I went around once, and then I told it to repeat it 3 additional times. So just got to remember that it'll keep building. Now, in this scenario, to get to a desired depth, I do have to make sure that my numbers stack properly. So certainly, if I was to have told it that, I'm going to, maybe I wanted to go down on a number that wasn't evenly divisible, I would have to figure out and divide the total depth by that number and make sure that each pass is the same. But this is a quick little simple way to be able to take features and get them to start shifting down. Okay, so I've built up my shape. I'm now going to continue writing my program. So the next statement that's pretty commonly used when I'm going to start to tell a machine to kind of move or retract, get to some safe stop point before I do a tool change or an end of program. A lot of times I'm going to want to shut my spindle off, maybe shut my coolant off, and then I'm going to use what's called a SUPA statement. And we have a couple different commands that do very similar things. SUPA is just the highest level. We have G53, G153, and SUPA. You'll see different ones posted from different cam guys all the time. Really, SUPA is probably the best one they should be using because that suppresses all of the offsets that are currently active. So it's really what it's doing is it's saying, hey, don't use your G54 right now. I want to position based on the machine coordinate system. So when I do a SUPA, I want to cancel my tool offsets. So I use a D0 to cancel the tool offset. I want to give it a rapid command in this case because I want to remove fast. And I'm now telling the machine to position to machine 0. So it's important that you do know where machine 0 is on your machine because that's where she's going. This is what we call a non-modal statement. So on the next line, the G54 will be reinstated. However, the D0 is modal. So if I know that I'm going to need to use this tool 1 again, I would reinstate it by giving it a D1 after this line. But in this case, we're going to be doing a tool change immediately after, so this is not an issue. Now, you saw earlier we did a tool change just by discretely typing the tool change. Well, once I want to use names, I don't want to have to do the T equals quotes like you saw before every single time. So if you're on the edit page and you make sure your vertical soft keys are back at the original state where your cut, copy, paste can expand, you get a button called Select Tool. Select Tool, by hitting it, shows me the list of tools that I've predefined. So now, if it's time to drill some holes, I can just highlight the drill, say OK. It'll automatically put in the instruction for me. I use my D1 again. Always use D1 until you get used to using multiple cutting edges. Give it your M6. Fire up the spindle at some speed. Now, in this example, in drilling, I don't want to drill in inches per minute. I want to use feet per rev, because quite commonly in drills, I know the feet per rev. So if you just type simply a G95 and then what my feet per rev would be, I'll do 3 thou per rev. Now, every rotation of the spindle, the machine's going to advance 3 thou. Okay, so my spindle's fired up. I am ready to start drilling some holes. Now I'm going to explore the first can cycle you're going to get a chance to see. So we're going to go to drilling, and this is a series of all of our can cycles. Now, unfortunately, with the time allotted, I don't have the time to go through each of these cycles, but what we will do is we're going to go into the basic drill reaming cycle and drill some holes. So you're going to come to the cycle, and you're going to fill it out. And if you've watched the earlier shop mill webinars, you'll know that the variables here are the exact same variables you had before. There's only some slight differences, like retract planes and safety distances. Those are traditionally done in the header page of shop mill. Since you don't have shop mill and there is no header page in this program, you just have to fill those couple out. Also, we're used to having to tell the tool in the cycle in shop mill. You don't do it here because the tool is pre-done prior to this, like you just saw with the tool change. Other than that, all the variables are exactly the same. Top of the part, where am I starting? How deep do I want to drill? How do I want to drill? I had told you earlier that the system can compensate for the tip of the tool. That's why I told it I had a 140-degree tip angle. Well, I could tell it, do you want to compensate for it or not? So I want to compensate for it. Now, it's important that you set up this option from single position to modal call. Modal call sets up allowing the drilling cycle to apply to multiple holes and multiple positions. If it was in single position, it would just drill wherever she's currently sitting. It's a one-shot deal. So by clicking modal call and hitting accept, I now get an M-call statement on this can cycle line, and that is now modal. It's going to keep on doing whatever I want it to do. Now, a simple longhand way of physically telling the machine where to drill, you can literally just start calling out the positions. So if I look at my print, I have my first is at 625 over and a Y of minus 0.625 down. And then you're just going to give it a bunch of position moves. Rapid is modal, so I don't have to keep telling it. I can tell it to go to my, now in this case, I can do the math. I can do an incremental shift if I want using that IC. I'm just going to do the math, so I'm going to go over to 2.125 for my X location. That would be this hole right here, right by that radius. I'm going to do a 2-axis move now, so we're going to go to an X of 3 and a Y of minus 2.375. And then our final position is going to be going back to an X of 1.5. So you can just keep randomly giving it as many holes as you want here. Now it's going to keep on drilling until you give it a M-call statement by itself. That's how we shut off any modal commands we've turned on. Traditionally, we're maybe more used to that, like a G80 and some other controls where you cancel drilling. For us, it's called M-call. So you type in M-call. Anything sitting between these two statements is what you're doing, is what you're modally applying it to. Okay. So I drilled some holes. I'm probably going to want to shut my spindle off and do the same routine I did before. So now you can start to use your cut, copy, and paste functions here. So if I bring my cursor up, click on the mark button, I can actually highlight whatever I want. I would use the blue arrows to toggle it around. Once it's all highlighted, I say copy, bring my cursor down, paste. So you can start to duplicate the same features pretty quickly in a part program just by using the simple copy paste command. Now you'll notice it's not going to keep doing my sequence numbers. So if I want them to continue on, I would just go back and hit renumbering, and it would resequence the whole program. Now the only thing you want to be very careful of with the previous repeat statement is that you didn't add a line and it mess up the number call, because certainly I would have to then update that. So now if I start to look, I should have some 4 holes drilled. So we're going to come in and we're going to poke out a few holes. There's our profile around, and then we're drilling 4 holes. And I went a full 3/4, so I should see daylight, and I do. I see daylight through my holes. So it went 3/4 of the block plus the projected drill depth, or drill point, shall I say. Okay, so we've profiled, we've drilled some holes. We're going to jump back to edit. Now we're going to go in and we're going to continue on. We're going to counterbore some holes with our end mill. So what we want to do is I want to now position to my 3/8 end mill. So I'm going to let the M30 keep on pushing down. So we're going to go back over to edit, make sure I'm at my first page, get my 3/8 end mill. D1, we'll do our M6. Once our M6 is in place, we'll fire up our spindle, whatever I want to run it at. Not too concerned about speed of feeds. Now, the G95 is modal as well, so it's going to be on until I tell it otherwise. So if I want to go back to inches per minute, I definitely want to tell it right now. Once I've fired up my spindle, maybe put my coolant on it if I wanted it from like before, get my feed set up. Now I'm going to tell it that I want to mill some pockets. So I'm going to mill these 4 holes as pockets. So I'm going to go to our milling cycles, and we're going to use our pocketing cycle right here. So I go to pocketing. Once I'm in pocketing, I would come down and pick the desired pocket. In this case, I'm going to do a circular pocket. So give it some retract planes. Where do I want to go when I'm done? How close do I want to get when I start feeding? What is the feed weight I want to run the pocket at? And then what do I want to do to the pocket? So in this case, I want to rough out my pocket. We can do a helical cutter pass. We can do centric or plane by plane. So I can pick a couple options. My position pattern. So this allows me to use milling cycles with the M-call statement as well, or modally. A single position, just like the drill would do 1 shot. But if I select the position pattern, now I'm only going to tell it the top of the pocket, the diameter, the depth of it may be, what my step over is. Since I'm helically milling, what is the pitch or the spiral as I'm coming down? How much am I advancing in Z? But once I set this all up, I can treat this just like I built the drill before. So M-call, and then I give it the positions. Now, I showed you the longhand method of creating positions by just typing them out. But what if I wanted to use one of our cycles? Well, I can jump back to drilling, go to positions, and now I can pick random locations. I can pick arrays of holes. I can pick bolt hole patterns. So we have a whole bunch of scenarios. So what I've pre-set up, for example, is a drill position, and I've created a label here. And this is only important if I want to do different operations on the same set of holes. So you'll see it in a sec how I can use this label to call them up. So we type in drill position, or whatever you want the label to be called. It's solely up to you. The default plane, what direction is the tool pointing in. And then I gave it the same locations I gave it earlier. So just defining my 4 positions. So position 0 through position 3. That will give you 4 locations. You hit accept, and now it builds it as a cycle. And I can chain as many of these cycles together as I want. So if I want to drill some irregular pattern and then go the same bolt hole pattern all with the same depths, I could do that through these cycles. Now, just like before, if I turn it on modally, I got to remember to shut it back off. So I'm going to give it my M-call. And now I will get a counterbore at each of the 4 pockets. So now I'm going to continue on. We'll finish up the program, and then we'll simulate it. So the next thing I wanted to do was I now want to go back, and I want to chamfer or counter break that counterbore with my center drill, because it's a nice, simple way to do a simple chamfering cycle. So what I'm going to do is we're going to do kind of like the statement we did before. I'm going to shut my spindle off, maybe shut my coolant off if it had been running. Just to show you a different way to position, I can certainly use the SUPA or the G53 or 153, but we can also do something called a G75. G75Z0. And what that is that's actually saying use a predefined position that was set up in the machine parameters to go as a reference location. So the builder can set up to 4 positions. So you can actually toggle between G75 index 0 up to your index 3 or the 4th position. But you do want to make sure before you use a G75 statement that the builder has set it up and set it up properly instead of just blindly going to some location, because this is referring to a location in the system parameters. But a lot of guys will use G75 for like tool change location. So it's a nice, quick, simple way to get the head up, at least to a tool change location, up out of the way without having to maybe write the SUPA statement. Okay, so we're going to go back and do our tool change. So I'm going to select Edit and Select Tool like we did earlier. And now I'm going to use my center drill. So we will allow you to drill, or mill, shall I say, with drills. That's okay. You just can't program feed per tooth, which we'll hopefully, if we have time, get to in the next example. I know we're running a little long on time here already. So anyway, so in this case, I create my call, my tool change, right? I call up my center drill and my D1. I give it my M6, as I've done so many times before. Fire up our spindle. Give it my M3. I'm still in G94, so I don't have to tell it. If I wanted to run a different feed than F20, I could tell it here by itself. I could tell it the can cycle. Up to you. So in this case, we're going to go back over to milling now. We're going to go back to pocket, but we're going to use the option we had earlier, which was chamfer. So as long as I'm chamfering in an inch per minute mode, I can use a center drill chamfer, and it actually works quite well. Now, when you build the chamfer cycle, it asks for the top, asks for the rough diameter, obviously the diameter of my counter bore like I put from earlier, but then it asks for the size of the chamfer and the depth. So FS would be the size of the chamfer, so I'm doing a 25 thou chamfer, and then so I don't have the tip of the tool right at the edge of the chamfer. I'm going to insert it just a little bit deeper, so I'm inserting it 0.75, so I should have another basically 50 thou below the tool tip. Now, if I use a center drill, it's assuming, it has to assume that this tool tip is pointed. So there's no flat at the bottom of this. Later example, I'm going to use a chamfer mill, and that would have a defined flat. So in that case, you set it up slightly different. So just remember that. If you're building it as a center drill, it's going to assume it's pointed. So if it's not pointed, if it's not coming to a full point, there could be some discrepancy in that size. So you fill out a cycle just like we did earlier. Place it in. Now in this case, since I used the positions and I used this drill pause label, I can use position repeat to call it back up. And that's where the label comes in. You just type in the name of the label, so just make sure you put something you remember and type quickly. And this repeat drill pause statement will say, hey, go look back. Did you see anything that was called drill pause? So I could use this for all the holes, and that's normally how you would do it. So just like earlier, I need to shut my drilling off with my MCall. Maybe I want to do my SUPA statement here, so maybe we'll come back. Now, if you grab pieces of the program that have sequence numbers on them, all right, like I'm going to do right now, and I place it down here, it will obviously paste those numbers in, so they're not duplicate. But if you simply renumber, it'll just correct all of those for you. So we've now built the program. We're going to go to simulate it. And you're going to see it's going to, again, do our profile, drill our holes, but now we should get the counterbores with the end mill. All right. And then we're going to chamfer mill. It looks like I just needed to add a little retract when I went back to the start point. That's most likely because I'm sending it to a G75, but I haven't actually given any offsets on the part, so everything's actually working all the way up at machine 0 is kind of what's going on there. But what I do want to show you here is if I go to our, details view, You can do a cut view, and I can stage my cut, move my little box around wherever I want to get it. But now you can see, and we're going to zoom right in from the side here, you'll be able to see our, let it refresh here for a second. You'll be able to see the chamfer that we just put in with that center drill. So that's just a quick, simple way to show you guys how to start to do chamfers and breaks on different features. So you'll see a lot of the cycles in the system have the ability of doing chamfering like that. Okay, so we've now built our first example. I know we're right at the 1 hour mark. I did allot this seminar to go an hour and a half, so hopefully you guys have the time to hang with me. So we're going to jump back over to our slide deck, and I'm going to minimize the print for now. And now we're going to talk about our more advanced example, or what we call example 2. So we're going to do the same process, but we're going to use some additional tools and functions that you have available here for you. So first thing I want to do is I want to go and do a facing cycle. And we're going to get a chance to build a face mill here. And I wanted to build the face mill specifically because there's some additional information that's needed in a facing tool. Outside of what we've already seen created when we created the basic end mills. So we're going to get a chance to use a facing cycle. Next step, we're going to actually go and start calling up outside programs as subprograms. So we'll have created a little program to handle not only the drill positions, but we're going to also make a little program to handle our retract. And we're going to build them as subprograms. So this would be kind of the structure that you're going to see here in a second when we want to start using subprograms inside of main program files. Then we're going to go in and we're going to show you how to do the exact same milling profile, but now we're going to use the contour editor to actually machine this profile. And you're going to see that it's just going to give you a lot more power and flexibility than certainly doing it the longhand way that I just showed you. We're going to then have the ability to even come back up and put corner breaks now on the outside profile since we used the contour profile function. So we're going to come back and we're going to do chamfering, and we're going to do chamfering with a tapered end mill instead of a center drill. That allows me to start to position it with feed per tooth, and it also allows me to define the bottom flat on the tool so I more accurately get a representation of that tapered end mill or that chamfering tool. And then we'll certainly jump over. So you'll see in this next example, we even have an outside corner break or an outside chamfer around the periphery of the part. That allows us, since we're using the profile milling cycle. Okay. So let's jump back over to our Sinutrain scenario. We're going to bounce out of this program. So I'm going to just hit the Program Manager, because we are now going to build a new program, and the new program is going to be based on the same sample, so I'm going to call it example 2. All right, so we type in the name, we select OK. We're now building a program. So the start is going to be the same way. So my same type of header that we saw before. So I'm going to do a G17, a G90, so the orientation plane, absolute positioning, G700, G54. The order of this makes no difference, whatever you get used to. I always find myself changing it every now and then. Now, we said that we were going to face off this part first. So if I want to go select a facing tool, actually, you know what we're going to do? Before we do that, we might as well get out of our way. We might as well put the blank in. So I'm just going to go back to the same page I had before. It actually even retained the same data, and just insert the workpiece blank. That'll get our solid model, so we're not going to see just the wireframe this next go around. Okay, so I want to get a tool, so I select the Edit option again, hit the Select Tool button in the upper right-hand corner. Now, we've been grabbing tools that were pre-created, and I do happen to have a facing tool that was built, but we're going to build it. So if you want to get all the way back to the tooltip of the build, just hit the Tool List button a second time. Puts us right back to the facing or the offset table, and now I can come down and we can build a tool. So let's say we're going to build a face mill. So I'm going to select New Tool. I'm going to select Face Mill. and I'm going to call this, let's say it was for argument's sake, it was a 2.5-inch face mill. So I'm going to type in 2.5 here just for my notation, and I'll tell it it's IN because it's an inch face tool. So whatever name you want. Now, I'm going to place the actual cutting diameter of the tool, not the maximum diameter. So if I have a face mill that has like an insert raked in an angle, that's okay. We can accommodate for that. But we're going to accommodate for that. You're going to see in a second. How many flutes or how many inserts do I have in the face mill? So we'll say this is a 4-fluter. So what you'll notice here is I get this further data button that pops up. Well, when I was on some of the other tools, there is no further data button. So when we get to tools that require a little more information, you'll get this further data. So always keep an eye on that and go into it. So in this case, it's asking what's the true outside diameter of the cutter. So I'm going to tell it it's 2 3/4. And what is the angle of my insert? So I'm going to say this has a 45-degree pitched insert. So now the system can compensate for that. So if I tell it to go right up to a wall, let's say, it'll make sure it stays away, in this case by 1/8 of an inch, so it doesn't crash the system, crash the machine. So I build the tool, keeping an eye on that further data. I tell it to program. It's going to insert the tool just like it has up till now. We'll do our D1, give it our M6. All right, so now, when I got to this scenario, when I'm about to face off my part, maybe I want to explore a different type of feed mechanism. Maybe I want to program feed per tooth because I happen to know that, the insert recommends that this thing run 8 that per tooth. Well, you can do that in R control as long as you've filled out the number of flutes in the tool data and the diameter of the tool's there, because we certainly need that to calculate. I can type G95. And instead of doing F like we did before, we're going to do an FZ equals. FZ equals signifies feed per tooth. And now I can tell it 6 out per tooth or whatever I want, and the system will automatically compensate and give you the correct feed rate. Certainly we need to start my spindle. That could have been prior to or after. So we'll run this at, say, 2,000 RPM, M3 direction. Once I've typed in the spindle, got it fired up, now I'm going to jump over to milling because I'm going to use a facing cycle. So we have a can cycle for facing. And the way this works, I come in, just like you kind of saw before, start to fill out the page and define where I want to go, what I want to do. If there's options, take a look at these vertical soft keys. Always keep them in the back of your head or in the corner of your eye. So in this case, let's say, I'm telling it to completely offset off the part. But maybe there's a wall here. So now I can tell it. And since I told it the true diameter of that tool, it'll make sure that it stays off of it. Now in this scenario, it's saying, well, you might not want to cut in this direction because you're going to leave these scallops. So that's just, see right here, it's indicating a little red dot on the cutter direction. So if there's something that it doesn't think should work properly or will work right, it's going to warn you, it's going to give you a little message, it's going to take the accept key away. So the system's trying to kind of guide you through. So like if I change my cut direction, now it's happy because it's not leaving scallops. Or I could have left it the other direction, but maybe used a different scenario. Or maybe told it to gate 2. So you'll always kind of play around with it and kind of watch what it's telling you. You should navigate through it pretty well. Now the feed here, it's going to use whatever modal state you're in. So if this is in feed per tooth, I would type in the appropriate feed per tooth. I said 6 thou. If it was inch per minute, I was programming an inch per minute value here. Machining state, the little symbols. Roughing is a single diamond. Finishing is multiple diamonds. So what do I see happen? Well, in roughing, it leaves the cutter on the part engaged the whole time. So this would be just kind of the example of the cutter path. If I'm finishing, it's going to allow, it's going to allow the tool to fully come off the part, wrap it to the next position. The other thing that finishing takes away is the ability of doing multiple cuts in Z. See the DZ field right here? That goes away when I'm in finishing. Other than that, to build the cycle, you're going to just define a couple positions. All right? So I'm defining 2 corners, so I'm staying just slightly off the part. Top of my stock, the other side of the part, so I can define it incrementally, I can define it absolute. The ending position, what my step over is, So I'm using either the percentage of the cutter, or I can toggle it to a linear distance. To toggle any of these fields, you just hit the select key to toggle between them. So I'm going to use a percentage of the cutter diameter. And then do I want to leave material for a finished cut? So once you've defined it, you hit accept. The cycle is now in. I'm going to take this little space away. And we're starting to machine, or we're starting to make the part. So this would handle facing off that part. We're going to now continue on because I want to change the tool, get the end mill in it like we did before, and then we're going to profile it, but we're going to profile it with a different cycle. We're going to actually use the contour milling cycle. So the next step is going to be doing that retract, the safe shutdown, and pulling my tool away. So why don't we use this as a great transition to start to show you how to build subprograms. The subprograms can exist in different ways, different areas in memory. They also don't even have to be an actual subprogram file. They could be a main program file. We accept either one. In this example, to keep it simple, I just decided why don't we give you a couple examples of a subprogram in the subprograms directory. So what I did was I had previously built a quick little cycle called retract. I just named it retract. Now, any programs I build in the subprogram directory only allow G-code, can't be conversational, and they're automatically going to have a .stf extension. Other than that, it's going to be the same scenario. So here I went into my editor, gave me a basic editor, and what I did was basically I gave it what we've been using. The M5 to shut the spindle off, the M9 to shut my coolant off. I used the superscript statement. This certainly could have been that G75 I was talking to you about earlier. And then I gave it an end. Now, when you are doing subprogram files, meaning it's got an SPF extension, the end of program statement is going to be stated as an M17. This is an end of sub return. If this was built as an MPF file, I would still use an M30, and then as long as, once I'm calling it from another program, it understands that the M30 is just returning. So you'd use an M30 if it's an MPF extension, but an M17 if it's truly an SPF extension. It's the only difference. Other than that, it's going to be the same cycle. I can use all my CAN cycles here. So all the stuff you're seeing, the drilling cycles, the milling cycles, can be used in the sub level as well as the main program level. Now, once I've created the program and it exists in memory, so in this case it's sitting in the subprograms folder, when I'm in the middle of my program and I'm ready to use it, all I have to do is type the name. So make sure you use a name that you remember how to spell. So I'm going to use the name retract. I don't need the extension. It's not required, so I don't have to put the .stf. I just type retract. The system will automatically search the memory as long as the file either exists in the part programs, subprograms, or the folder that your main file is in. It will call it up and use that file. Okay, so we type in the name. Now that sent the head up, shut the spindle off. Now I'm going to do my tool change. So I'm going to use the same tool, but I want to show you what would happen if I used the mechanism to load the tool. It would give me my T equals. Either one works. So I could have typed T1 like I did. If I don't remember what T1 was, or I want to look at my tool table, but I still want to use numbers, absolutely okay. It'll just automatically put it in as a T equals quotations 1. Either one's going to call it the exact same tool. All right. So we fire up my spindle. We're going to fire up my spindle now. So whatever, 3000, let's say, M3. All right. Maybe I want to jump back to inch per minute mode. So I can go back to a G94, back to my normal feed. So we'll say 50 inches per minute. Okay. Now, we're about to build our first contour mill cycle. So the structure here is important. I did want to make sure that we step through this portion. So what you're going to do is you're going to give yourself probably a couple blank lines and give yourself an M30. Because what you're going to do is you're actually going to build the contour after the M30. And then the system will then call it up when it's time to use it up top by using a cycle call. So you're going to see that here shortly. So just give yourself an M30, leave the cursor sitting below the M30, go to Contour Mill, and now you're going to go into the Contour button, and you're going to select New Contour. New Contour first allows you to give it some name. So I'm going to say it's my, I don't know, OD. OD, part, whatever's reference for you, just a name. So you type in the name, hit accept, and now this is going to give you the same contour editor that we've all seen and used in ShopMill from the earlier examples. So really, I'm going to draw the part like I normally would. So 0, 0, starting location. I'm going to use these little icons to draw the shape. So my shape goes over 2 inches. I'm going to do an arc. It's going to be a clockwise arc with a radius of 1.5. It's ending at 3.250 and a y of minus 1.802. We'll get the dimension correct. Gives me my 2 different scenarios. Did I type that wrong? Nope, I didn't. So which of my 2 arcs I want to use? I want to use the smaller of the 2. Accept it. So we got my 3.250, my minus 1. Oh, nope, I did use the wrong one. Look at that. Typo. See, I'm trying to do this too quick. All right. So I can always go back to this change selection scenario. See, I did it again. Forgot my negative. This is the beauty of graphics. Okay. So now I see I can always get to this whenever there's more than one option, because there's some trig help going on here for you automatically. You can always get back to the selections by hitting the change selection. So if you type the numbers in wrong, you've got to manipulate them. Perfectly okay. Just go back and make sure it's still picking the right arc. So I wanted the little one. Accept. Now we're going to do a 2-axis move. We're going to go all the way over to 4 inch. We're going to go all the way down to our 1.802. It's time to use that one. What's nice here is I get that graphical representation here immediately. So like before, I had to go all the way out to simulation before I saw that I had made an error. So in this case, I'm going to do a chamfer. So it's going to work just like the CHR statements you saw earlier, but it's just doing it all graphically in this little tool for you. So we're going to move back to 1 inch with a radius of 0.5, and we'll just finish this up pretty quickly here. So x going to 0, y going to minus 1.5. I'm going to do another 1/2 inch radius. And then I'm going to complete it by going up to y of 0. So I draw the exact shape. I don't have to worry about lead in or lead outs or any of the stuff that I had to do earlier. Now I simply hit accept. And what you'll see it'll do is down here below the M30, it built this little grayed area. This is how the contours look in G-code. You never have to edit them as far as in here. What you would do is just make sure that the highlight is somewhere within this grayed area, really between these 2 labels, the OD and the bottom OD. And then you're just going to hit the blue arrow to the right key over, and you go right back to your editor. And this edits just like it does in ShopMill. So everything we've shown you in the past still applies here, no differences. But what changes is when it's time to use it. So I'm going to move my cursor back up to my main program, just below, in this case, below my feed call. And I'm going to use the call contour function. So that's when it's time to use it. So I called mine OD. So I type the name OD, hit accept. And the cycle 62 is what searches memory, goes and finds the contour. The contour can be in the program, can be out of the program. There's all kinds of different places it could be sitting at. Okay. Now, it's still not going to machine anything. It's just loaded the contour. So now I got to back up, and now I got to pick one of my 3 primary cycles I have in contour mill. I can do path milling, which we're about to do. I can do irregular pockets, if this was a pocketing routine, or I can do boss milling or spigot milling, where I would leave the boss standing. We are, in this scenario, going to do a basic path mill. So I'm going to select path. I'm going to tell it where to go when I'm done, fill out my normal variables, feed and speeds. Do I want to follow the direction I drew it in? I establish my cutter comp here. Top the part, depth. We'll say we're going a 1/2 inch deep. That's fine. Depth per pass, maybe I'll take this in a couple cuts. All right, do I want to leave material for a finished cut? Now, what is handy here is, right now we're going to do it in one shot, but what happens if I cut it and I'm leaving material standing, which we're going to see. I can kind of play around with the cycle a little bit leaving material for a finished cut. How do I want to lead on and off of my part? So I'm going to lead in with a semicircle, and I'm pulling off with a quarter circle. Happens to be using a 1/2-inch radius, and I dropped my feet a little bit. So you fill out the page, you fill out the cycle, you hit accept, cycle's in. So if I start to simulate, now we should start to see what's happening here. So I'm going to face off the part, and I want to get rid of, my cut view we don't need. Okay, so I see my little lead in, my little lead out, gives me a much more proficient cutter profile. There's our little facing operation. I run it before, I run it one more time. I'm going to zoom out. So you see there was even a little chamfer there on the facing tool. I've compensated for it. Now, before, getting rid of these little corners would have been problematic, obviously, with the way we did it in the first example. But when you start to use the profiling cycles, it's actually pretty quick and easy. I could just say, hey, you know what? I know I got some material out here. Why don't I just do one pass around it at a larger value and then do a second pass closer? So I can start to play around and chain these different cycles. So, you know, I could have said on the first one, leave, I don't know, let's leave a 3/8 of material on the side, and then did the cycle a second time, bringing it right to 0. And it's just a quick, impromptu way to kind of set up and set in multiple roughing passes in my X and Y instead. Certainly, I could use the spigot cycle to do this type of function, probably the more preferable method, but I don't have to. You get a lot more flexibility when you start using these contour profile editors. So there you see, we rolled around the part. We did our different profiles. So just a couple of things we want to show you here as we're kind of running low on time. So I do want to do my retract statement. So here's my retract. I'm going to copy that, paste it here. Send the tool up and away. We're going to do a tool change because we're going to drill our routine or drill our holes. So I'm going to now, I'm going to cheat a little bit just for time's sake, because I know we are running low on time. I have previously created this scenario, but I'm also going to show you kind of a neat trick, especially if you start to, have common operations that you do a lot. You can actually open multiple programs in the editor at the same time. So by being on the edit button and double clicking, I have this open further programs field. So if I go to my part programs and I go to my ProgramGuide Milling WebEx Example 2 I had previously done preparing for this course, I can bring up the job how I methodized it before. So what I can do here is I can now start to use segments or features of the program. So what I'm going to do is I'm just going to copy and paste in some of the stuff that we want to do here instead of us writing it all longhand. So I'm just going to grab all of this stuff down here. Come on down. All right, so we'll bring it right down to the M30, which I already have. And now it's a matter of cut, copy, and paste. So we got to love copy and paste. It's a beautiful tool. We just made a program really quickly. Okay, so what I wanted to do is I just kind of wanted to show you, you saw the structure, tool changes, calling up a cycle. None of this has changed, right? This is exactly the same way I just showed you. The only difference here is I wanted to be able to call up the routine, the position routines from an outside program. So just like you saw me do the retract, what I did was I had previously built in subprograms a little program called position drill. It could have been the rapids. This one I had even handle the M call. It could have had the cycles like we used before, the position cycles. It really can be anything you want can be called up. But the big takeaway here is certainly to start to see that I can have all sorts of different types of content being called up. In this case, I'm just calling up a drilling cycle right in the middle. Now I had the M call already in there, so actually this M call was redundant. It's not even needed. There's my retract. We're loading up our 3/8 end mill, so it's going to work the same way. Here we're doing our. Now In this example, I wanted to just show you a different way of calling an outside subprogram. So previously, you saw me just type the name, position drill, and it looked to the outside. We do also have a function under various called subprograms. So that is this event right here. So that was built with that subprograms field. So if you want to actually use an event screen to type it in, or you forget how to do it, you can come in here, you can type the name of the cycle, and that will insert it as a call statement. And that's as well going to look out and call up that routine. Now, the final scenario we did is we come in and I built a new tool called chamfer mill. So chamfer mill is not a center drill. So we're using it the same way we did a center drill. We're going to come into our pockets and we're going to do a little chip breaking cycle or relief, but we're going to use, in this case, a tapered end mill. So the way that tool was built, and I think I still have it built, I do, is I built that when I went to New Tool, I used the bevel cutter option. And by picking bevel cutter, that creates this tool. I called it a chamfer mill, and it gives us our further data function. So there's just a couple things I want to point out when using tapered end mills. First, the diameter here is not the major diameter of the tool. It's the bottom of the tool. It would be the flat of the tool. So in this case, I'm saying that this tool has an 1/8" flat at its bottom. And then when you go into further data, this is the angle, but it's half of it. So it's not the full included angle. It's per side. So if I wanted a full 90-degree chamfer mill, I would type in 45 degrees because it's a tapered end mill at this point. So just keep those two things in mind. Make sure you go into further data when building tapered end mills and give half the angle. And also make sure that the diameter you give it isn't the major diameter, it's actually the flat, because that's the critical diameter for us, because that's how we're figuring out where the cutter compensation is. We don't care if it was a 1/2" chamfer mill. The 1/2" is the shank that's sitting in the collet. That doesn't mean anything to us. We need to know what is the diameter at the tip of the tool. Okay. So if I jump back in, we're then using it. Now, I did something a little different here. I not only came down here and did the pocket routine, but I also go in and recall up the cycle and use this cycle 72, which was the original cycle we used up top, right there, to then do our chamfering. And I'm using a repeat command. So this was just showing you a different example of calling up some position routines. So I need to validate that that is still accurate. So I'm going to renumber our routine. Actually, I shouldn't have to renumber. We should be okay. So this is just saying, hey, go back up to line N150, which is my position call, and also do N155, and just repeat it. So this is just another way of grabbing data and doing it a second time. You saw the kind of the repeat command with the loops earlier. So same concept. So if we simulate it, we should go through and get our base. Of course, I probably called it something a little different. So let me just go back in. Remember, we rebuilt the tools. So I bet you this tool doesn't exist anymore, right? I called it something different. Yes, I did. All right. Copy and paste. Gotta love it. All right, and then the 3/8" in general should be the same. So that's kind of where the error trapping would start to come in. It was validating the tools I was calling up in the part program, telling me that that tool doesn't exist anymore because I had deleted it and I gave it a slightly different name from when I first did the example myself. So we roll around. If it gets a little muddy with the show path on, like we turned on earlier, I can always shut it off. So now you see the tool come in. Here's our chamfer mill. And there's our chamfer mill walking around the perimeter as well. So the big advantage to the chamfer mill is I can actually program it either inches per minute or feet per tooth. So in this one, actually, I had programmed it feet per tooth. So that same statement you saw earlier, the FC equals, I can do that with the chamfer mill because when I look at the end mill, when I built it, I do tell it the number of flutes. If you define it as a center drill, it doesn't know number of flutes, so you can only program inches per minute. Okay, so we had a lot of content. We certainly used all of the hour and a half. I'm not in any rush here, so I'm going to, at this point though, I think we'll kind of end the content section, because I did want to give you guys a chance, if there were any questions, to fire out some questions on the content before we end up this session. So, without further ado, if there's any questions, please feel free to type them into the Q&A panel. We have some here already, so I'm going to just take a quick look, and we can maybe get through a few of these. All right, so I did have one person ask, they had some difficulties in the beginning of the presentation. If we have time at the end of class, could we please recap the first tool? So he probably was referring to the first tool change. I would think that we probably went through that since he typed this in, because this was typed in a while ago. If not, please re-enter it, and we can cover it again. Can you email me the finished programs and subroutines? Absolutely. Best scenario would be if you can send me an email. That would be great as a reminder, and I can certainly send you out the subprograms. And you can use them on your own, absolutely. And certainly they can be brought right into a machine if you want. Okay, so can you use subprograms to run measuring probes? Absolutely. Yeah, really any routine that we use can be called up from a subprogram. So if you wanted to create your own, you can even create your own cycles if you want, and they could be called up as subprograms. So yes, you could certainly run them as measuring probes. Pat wrote N97M5. So I'm not sure what he's referring to. I would need a little more detail, Pat, if you can. Luke, what is MoldMaker View? Luke asked that. That's a nice little feature here, and what it does, probably better off shown in example 1, but MoldMaker View will analyze and give you a quick little snapshot wireframe of any of the line moves in a part program. Better example, and I don't think I have it in this machine, unfortunately, would be if this was a surface file. I would actually see, under MoldMaker View, I'd see like an instantaneous snapshot of the wireframe of that part. So you can really get an idea of what the surface looks like. In our little example, we just have some lines as the perimeter, but you see this is the cutter path. So it's just a method of getting like an instant simulation without having to go in and run the simulator. Is it possible to make a tapered thread with ProgramGuide for milling? Okay, this is actually going to work the same way in either ShopMill or in ProgramGuide, as far as if you're using our can cycle. So the can cycle itself, so if I was to go into milling and go into thread mill, this is a straight thread mill routine. So if I want a tapered thread mill, I would use a tapered thread mill cutter. So the routine itself is going to do 1 or 2 or even a couple flutes, but it's not going to spiral out or in. So like if you wanted to generate a single point tapered, then what you have to do is, we do have cycles you can do that with, but you have to program that longhand. The standard can cycle, however, would require the taper being ground into the thread mill cutter. And traditionally, that's usually the way you'll see most guys would do it from a proficiency standpoint. To single point, like a tapered pipe thread, and generate the whole thing would take quite some time. But if you want to do that, you'd actually create a helix cutter path. The helical cutter path would be with an arc statement. And then you'd use a Z advance, and you can actually move out your diameter. And then you can even use a turn statement, but it gets a little more elaborate. Okay. Hopefully that kind of answered your question there. Is it possible to send the presentation and the programs as a package? Absolutely. If you guys would like a copy of the PowerPoint, I could certainly do that. Again, I ask, probably simpler for me because I get a lot of people register on these. If you could just shoot me an email, I'll respond back to you on an individual basis. If you guys need my email again, it's Chris, C-H-R-I-S, Pollock POLLACK at Siemens.com. All right. Good. And what do we got? Oh, Pat was asking, what is the proper syntax for the super statement? So he has a G0 super, Z1, D0. Yeah, the sequence of the super statement is not dependent, Pat. I myself always type super first, but it really makes no difference. So you have in your little example the rapid, then the super, then the Z positional move, and then the cancel D. It's fine. The sequence of events is not going to affect you. Traditionally, I've just always gotten kind of in the habit of doing the super, then I cancel the tool, then I give it the rapid, and then the Z. But it doesn't make any difference. It's certainly up to you. Okay, a lot of great questions. Well, let me see. Looks like there was another section here. Just make sure everybody else is good. And I think we got everybody's questions. If I missed anything, by all means, feel free to reach out again through email or through through the phone. Certainly, if you guys also want that little sheet I was talking about, that little reference chart, shoot me an email if you hadn't already gotten it, and I can send that on its way as well. Great. Well, thanks, everybody, for joining me again. I'll send out the link to the recording here shortly, and I hope everybody has a great weekend. All right. Take it easy. We're going to stop the recording now.